Welcome everyone to session 1D. Today's topic is continuity and discontinuity. So in our last video, we developed this idea of evaluating the limit by directly substituting or taking the value of the function at that point immediately. So while we said that we don't care about the value itself, it turns out that in most cases, that limit is directly related to the value itself. And so continuity at a point is defined as the following. An internal point in a function is continuous if and only if the limit at that point equals to the value at that point. So very intuitively, in general, if you draw a stroke that is a function, then if you consider, let's say, x equals a, and you trace it from left and right, and you agree on a limit, then you would find that the value itself is the limit. And this is what continuity describes. Now, we have special definitions for the left and right endpoint. So at a left endpoint, we say that this point is continuous if the value agrees with the limit from the right. And for a right endpoint, we say that it is continuous if the value is equal to the limit from the left-hand side. Now, actually, if you remember from our very first video that we had special definitions for the limit at left and right endpoints, we would see that the limit, the overall limit at a left or right endpoint would be defined as either this or this. So actually, we could just use this overall definition for all cases. But these just encompass all the possibilities to help you get a better picture. So this is continuity at one point. So let's look at a couple examples over here. So in order to tell if a certain point is continuous, we first want to consider its limit. If this limit does not exist, then there is no way for that point to be continuous. So this is first. And second of all, we want to consider the value itself. Now, if both exist and they agree, or like they are equal to each other, then we have a continuous point. So let me demonstrate this real quick. Let's say we want to consider x equals 0 if this point is continuous. We would, since here we're given a graph, we would find its limit by tracing along the graph, and it seems to be 1. So we have that the limit as x approaches 0 of f is equal to 1. But the value, and the value at that point is equal to 1 as well. So we have the limit, it exists, and we have a value, and it also exists, and they both are 1 and they are equal. So, and therefore we say that x equals 0 of this function is continuous. Now you can make the same argument for virtually any point on this curve, but there are a few exceptions. So for example, here at x equals 3, we have the limit tending to 0. So the limit is 0, but the value is -1. This is what we call a removable discontinuity. And so because the limit and the value disagree, this is an example of discontinuity. Discontinuity. And it means essentially that it's not continuous. Not continuous. Yeah. Here we have another example. In this example, as mentioned, the limit does not even exist, right? We have a right-hand limit that tends to 2, and a left-hand limit that tends to 2, and a right-hand limit that tends to -1. And so they disagree, and hence the limit doesn't even exist in the first place. And so there's no way for it to be equal to the value, or and even if the value also does not exist, they can't be equal. So notice that a does not exist is not equal to a does not exist. So for example, if I have something like this, if this is an open point, notice that the limit does not exist, but the value also does not exist because it doesn't appear anywhere here. So even if both do not exist, this does not mean that they agree or they're equal. Does not exist is not equal to does not exist. And so if you have two does not exist, that does not mean continuous. It's discontinuous. So let me formalize discontinuity here. So basically, we say that a point is discontinuous if the function is not continuous at that point. So they're exactly the same. So another quick example here is 1 over x. We've seen this many times. very intuitively, all of this is continuous, right? You can convince yourself as much as you want, but it is clear that at x equals 0, we have discontinuity because the limit does not exist. So the point of discontinuity here is x equals 0. So now we're going to talk about the different types of discontinuity. And in total, there are four main ways. Starting with the first here, we have the removable discontinuity. And this happens when the limit exists, but the value either does not exist or does not agree with the limit. So as mentioned up here, this value does not exist, or value is not equal to the limit, given that the limit exists. So what is so special about this type of discontinuity is that it is removable. And by that, we mean that we can remove this type of discontinuity by changing the definition of the function at that specific point of discontinuity. So for example, let's look at this. So here we see that the limit is clearly defined. The limit is L, but the value is M, and they disagree. So this is a removable discontinuity. And the way in which this is removable is that we can say that f of x, so let's say this is f, is equal to whatever's on the graph for x is not equal to L, but for, is not equal to A, but it is equal to L specifically when x is equal to A. So basically what we've done is we've moved this point down here. And effectively, we have removed this discontinuity by this special definition, and now it is one complete continuous function. Continuous function we'll talk about later, but you get this sense that at this point, it is now continuous through this removal. Here, likewise, we can define something here. We can define L at A, and that is the first type of discontinuity, the removable discontinuity. Now, the jump discontinuity is when the left and right limits exist but are not equal. And so this directly implies that the limit does not exist. And as mentioned earlier, if the limit does not exist, then there is no way for the value to be equal to it. And hence, this is in fact just one of the ways in which a limit does not exist. Here, for example, we have the limit from the left-hand side is, let's say, 0.5, and here roughly 1.6, let's say. But anyways, they don't agree. And so therefore we have a jump discontinuity. And literally, we are jumping from one point to another. The third one is the infinite discontinuity. This, again, is if the limit does not exist. The limit does not exist. And specifically, one of the sides tends to positive or negative infinity, and that leads to the limit not existing. So here we have some examples. At x equals 2, we see that the limit does not exist because left and right go to infinity, or they do not exist. Here we have, again, positive, negative infinity, and here, only one side is positive infinity, but still, that is enough to make the whole limit not exist. So again, the idea is that the limit from one side does not exist because of plus minus infinity. That's where the name comes from, infinite discontinuity. And because of that, the limit does not exist, and therefore it is not continuous. So this is infinite discontinuity. And finally, we have oscillating discontinuity. And this was sort of the last special way in which a limit does not exist. So still, a limit does not exist. And here we have the classic sine 1 over x that we were talking about. And again, the principle here is that the limit does not exist because of this oscillation. And because the limit does not exist, we have a discontinuity. Now, knowing what a continuity at a point is, we can extend continuity to over an interval. And we say that a function is continuous over an interval. Let's first say I for a closed interval AB. It can also be open, of course, if and only if f is continuous at all points of the interval. So it basically means that if all the points individually are continuous, in this interval I, then we call this whole interval I continuous. And this is still fairly logical and intuitive. Now, a continuous function is continuous across all points in its domain. So an interval is sort of like a local continuity. Continuous function means that it's globally continuous. So if you were to ask if y equals 1 over x is a continuous function, we would consider if all points in the domain are continuous. And one's first instinct might be, because as previously mentioned, we noted that x equals 0 is not continuous. This is an infinite discontinuity. And so from that, one might conclude that this is not a continuous function because it's not continuous at x equals 0. But notice the definition requires simply all points in the domain. And x equals 0 is in fact not part of this domain. And what is the domain is actually negative infinity to 0, union 0, positive infinity. And so this is the actual domain. And if we actually check or consider all the points in this domain, we would find that they're actually continuous because they lie on one of these hyperbolas right over here, here. And surprisingly, y equals 1 minus x is a continuous function. So that concludes it for today's video. We talked about continuity at a point and over an interval, as well as the types of discontinuity. In our next video, we'll be talking about the intermediate value theorem, which is the first type of problem that you'll see directly on an FRQ. And so this is going to be really important. Thank you.